Real life comparisons to vibrations, waves, and sound. The key concepts of my program. This is for our or my final project reflection. My name is Danielle Cameron, and today's date is May 7th, 2025. So you may hear some vibration, waves, and sounds coming from this fan above me. I'm hot natured and I need it off. So if you do, don't mind me. All right. Real so, um, in this project, I'm going to be sharing 4 physics concepts that really struck home with me. And this is how they show up in real life, especially in sonography, specifically cardiac sonography, which is the field that I am working towards. This presentation mixes the class material that we've had, some examples that we had in lab, as well as some concepts that really are going to make a difference whenever I do get into my major in the sonography field. And even everyday examples about things that we see or interact with on a daily basis. So, the first example that we have, or not the first example that we have, but the first thing that we'll be doing is just going over an overview of the items that we'll be discussing. The first item that we'll be talking about today is the Doppler effect. The second item is the Bernoulli's principle. The third is reflection and refraction in ultrasound. And the fourth is standing waves and resonance. So, the first one that we'll be talking about is the Doppler effect. And the Doppler effect is when frequency shifts due to motion, for example, sound waves and medical imaging. In the images to the right, for the car horn or a car sound, it shows how sound is emitted based on the frequency and the source. How does this apply to sonography? How does this apply to ultrasound? So, the same way you hear a horn or how you hear a siren or even an alarm on your car, right? It's the same way that images are produced using the Doppler effect. Another image that you're going to see on your right is the image of a red circle or oval and the image of a blue oval. When I was first introduced to this, I didn't know what it meant. Like red light, blue light, what's going on? But the red one is an artery and the blue one is a vein. This is something that's used in sonography. And in this example, so ultrasound images, they show how fast the blood is flowing and the direction in which it is flowing. So Bernoulli's principle is the principle that is applied to velocity and measurements to estimate the pressure gradient. So in this example, and as you see, it's a picture of a heart. It shows the right ventricle, left ventricle, right atrium, and left atrium. Um, this image is going to be something that we'll be seeing on a daily basis with cardiac sonography. So this Doppler of the echocardiography measures the velocity of blood flow using ultrasound waves. And the Doppler shift change in frequency is converted into velocity values. As you guys remember, we went over velocity earlier in the course. I think it was our second or third lab that we did, and we talked about how velocity affects how something falls or how quickly something moves. So this is important for IVs in the hospital, as well as the ability to measure blood flow, specifically in the heart, which is why I have this image of the heart there. And that's how Bernoulli's principle would apply. It's going to track that blood flow within the heart, within the different ventricles. Ultrasound images, they reflection and refraction. These waves include sound waves, and they're going to bend or reflect at tissue boundaries. These boundaries are going to affect the image resolutions. And I know you're wondering, like, how does this relate to sonography? As you know, sonography is nothing but images. We have to use images for absolutely everything. And so these images need to be clear for proper diagnosis and for being able to see the proper area. Ultrasound techs have to make sure that the probing areas are clear for correct diagnostics. This could be the difference between life and death, right? So reflection and refraction definitely is important. As you see, you can see a clear baby on the left-hand side, and then you see a fuzzy baby on the right-hand side. That's because that image is a refraction. It's not showing. Reflection and refraction. Standing waves and resonance. So natural frequencies amplify vibrations. How does this relate to sonography? In order to get the best images and the right frequencies when getting an ultrasound, you have to avoid artifacts. If you don't, it may interfere with the image. So common artifacts that you will hear about when it comes to imaging is like a pacemaker. That's why if you go to get an MRI and you're a woman, they'll be like, "Oh, do you have underwire under your bra?" Or another one that they'll ask about as far as imaging is concerned, a belt. Like if you have a belt on, they'll be like, "Hey, you need to take your belt out because it has metal in it." And this will all interfere with the vibrations, and it'll interfere with the image. Why is this important? Because in order to give someone the proper diagnosis, you need to be able to see everything. You need to make sure that the image is clear and that you're able to see what's going on, especially if that's the area of the body that they are going to be looking at. So this is why before getting an MRI, they ask, do you have a pacemaker? And they ask women to remove their underwire bras to avoid the interference with these images. Stay that's it. That's all. We went over 4 topics today. All of these topics are very important when it comes to sonography. Again, these topics are the Doppler effect, the Bernoulli's principle, reflection and refraction and ultrasound, and standing waves and resonance. All of these are stuff that we learned in physics that we are going to have to use, especially if you are in sonography or cardiac sonography. So let's wrap it up, folks. Time to go. It's been good. It's been fun. And it's going to be really fun when I get to get into my program after this. So what we know is physics has always been used and applied in real life to everyday scenarios like flying a kite or the infamous feather versus a book, which gets to the ground at a quicker rate. We've learned how information goes deeper than what we think and expanded on what we already know, what we learned. When I first began this class, I didn't know how physics would apply to my major. I honestly was annoyed at the idea of taking a course that I wouldn't need. That alone was enough for me to want to mentally check out. But this project was a final eye-opener about how physics applies to my program of study and its importance. What are we going to do with it? So chapter 7 gives me, and I hope others who are in sonography, an overview of how physics. That's it. What are we going to do with it? So chapter 7 gives me, and I hope others who are in sonography, an overview of how physics is important to sonography. Learning how the different concepts using sound waves and vibrations can be applied to everyday life in imaging is a necessary step to success in any imaging program, specifically cardiac sonography. So next, on the next page, you'll see some references